Good. Next thing, let's talk a bit about multivariate forecasting. I've already in the last section discussed what are the differences between global models and multivariate models. Machine learners have also invented a new name for it. They call it channel dependent instead of multivariate. As I've said before, it's not the same as global models. Here in multivariate cases, series need to be aligned. Often they have the same lengths. Also on our webpage forecastingdata.org, we have it kind of separated out. Yeah, and the main idea is that in multivariate forecasting, the series can influence each other. You can have cannibalization, substitution effects, halo effects, and so on. I think it can be considered kind of the holy grail in retail demand forecasting. It is a difficult and still quite active research areas, and the main problems that people try to address here is how can you scale this really to thousands of time series? How can I have series come and go? And how can I model just these changing and complex relationships, right? So yeah, and so usually the way to do that is with some sparseness constraints where you say each series can only interact with a few other series. So think about it. Let's say you are, I mean, I think this ETTH data set, that is, it has a couple of external variables, but maybe there are 7 variables or 10, right? So here it's a very different situation than if you say I'm a retailer, I have 20,000 products, so I have 20,000 time series, and now I want to train a multivariate model on that. Well, now one big question would be, well, I don't want to have everything influencing everything. So probably the frying pan sales are not going to influence the sales of trousers very much, but the sales of one brand of frying pan probably influences the other brands, and who knows, maybe you know, some food is influenced by the frying pans and so on. So, but the question is really, can we automatically detect which ones influence each other? Because you have to specify it in some way, otherwise it's not manageable. Yeah, so here some kind of more a bit older deep learning architectures in that space. So we have this 2016 paper from Yu et al., matrix factorization with temporal regularization. Then in Lai et al., LSTNet. That's a quite well-known paper because of that benchmark suite I talked about earlier. A lot of the data comes from this paper. And also this, if I'm not mistaken, this idea of predicting exchange rate 2 years into the future comes also from this paper. Okay, LSTNet, it's a CNN feeding into an RNN with skip connections. So the idea is I have here my multivariate input window, you know, that is shifted in that direction. So I run a CNN over that whole window, and then whatever comes out of that CNN, I feed that into an RNN, and the RNN kind of then steps through time. Yeah, Sen et al. 2019, matrix factorization, causal convolutions, and attention. And then, well, another proposal from 2019 are these Gaussian copulars. And then there are also some proposals using graph neural network. This second one is from my research group, because it's kind of obvious that, well, graph neural networks could be used for this. This first paper, their proposal is that you kind of learn the graph from the data, so you don't need to feed it in. And I think that makes sense, right? So as I said before, you don't want to have everything depending on everything, so you kind of learn which things are connected as a graph, and then you do your forecasting based on that. Yeah, so this was kind of pre-transformers in that area. There are obviously also transformer works in that area. Crossformer is the first one. The first multivariate transformer model. It explicitly models both the temporal and cross time and the variable-wise, the cross-dimension dependencies. We are two-stage attention mechanism. Then this one, this is again one from my research group, that's why I mention it. So here we have a transformer that uses sparse relation matrices, a reindexing scheme, and 2D attention. So again, the idea is that if you want to scale these methods up to thousands of dimensions, you need to sparsify, right? And that's what we did in this paper. And then I transformer here, the idea is the I stands for inversion. So it inverts the usual transformer structure. It applies attention over the variables instead of time. Yeah, again, getting better scalability. Okay, some software to mention in this deep learning space. There's obviously Neural Forecast, very nice library from Nixtla that has implementations of many of these deep learning architectures that I have mentioned. GluonTS, a bit earlier proposal from Amazon, also very nice, implements many things. I think Neural Forecast now is a bit more popular than the GluonTS. The GluonTS seems to be declining a bit in popularity, but yeah, certainly two very interesting and nice software frameworks to implement many of these things that I've been talking about. Yeah, a couple of data repositories and benchmark runs, just if you want to get a feel for which method might work well on your particular data set. There is obviously our repository at forecastingdata.org. We have many data sets, we have code and many results of statistic, traditional machine learning and deep learning methods. Then GIFT-eval that is based on, well, so it contains all the data in our repository. It is on Hugging Face, so it's easier for people to just submit their own methods. And it has a nice leaderboard. And then there is this quite new benchmark suite, FFDS, which is also on Hugging Face. It's from Amazon. And yeah, also a quite large repository and with benchmarks. Yeah, just to summarize this deep learning part, so there are certainly some very good methods out there, like PatchTST, Tide, that I didn't really talk about, TFT and others. They are worth exploring, but don't believe everything you read in these papers. The evaluations have problems. I've talked about it at many places. It depends greatly on the dataset characteristics of these models will work. So if you have large amounts of series, large amount of observations per series, definitely worth trying. If you have a single monthly time series, going to be difficult to train a transform on it. Yeah, you can check our evaluations on forecastingdata.org, where we ran many of these methods on different data sets. If you want to get an idea of what works, GIFT-eval will also help you in that respect.